All right. All right. So
Yep.
now we're going to move on to actually looking at the stars who might be doing the reionization. So the next talk is about carbon isotopes. Please go ahead.
Thank you. So hi, everyone. My name is Louise, and I'm a PhD student at Durham University. And I'd just like to thank the organizers for creating this wonderful online space, because I've really learned a lot already. And yes, so today I'm going to talk about some work that I've been doing with my supervisors, Ryan Cook and Michele Fumagalli, and one of our collaborators, Max Bettini. And the general idea is that you can use the chemistry of near-pristine systems to investigate the properties of the stars that enrich them. And not only that, but by looking at these enriching stars, you can start to look at the star formation history of these very metal-poor objects. And so a quick motivation for this search is that the first stars to form in the universe, these population 3 stars, have never been detected, despite surveys spanning almost 4 decades now. And so what we tend to do is look for the surviving chemical signature of these stars in relic objects. So if you imagine in this flow chart, there's a massive metal-free star in the early universe undergoing core collapse supernovae, and it's going to enrich its environment with the first instances of metals. And these metals will migrate to the now chemically near pristine gas, and then this gas will cool and collapse and form the second generation of stars we see in the halo of the Milky Way. And so this search so far that I've been working on is focusing on looking at the chemical signature of this near pristine gas. And to do that, we rely on a technique called quasar absorption line spectroscopy. So I just have a quick video showing how this technique works and what you see. So we're watching light from a background quasar travel towards our telescope. And at the moment, it's going through pockets of low density gas and creating the Lyman-alpha forest. But as you approach a galaxy with a large reservoir of neutral hydrogen, you get this really distinctive absorption feature with these damped wings. But not only do you get absorption from the neutral hydrogen, you get absorption due to the metals that are in this gas cloud. And so this is a really key technique that we can use to look at the chemical composition of gas in the redshift interval between 2 and 3, typically because this is when these objects are most easily studied. And so the DLAs themselves are quite easy to identify by these damped wings. And what we're really trying to do when we're looking for the first generation of stars and their chemical signature is to find the most metal deficient DLA possible. And these have metallicities almost 1,000th of that of the sum. And for this search specifically, we've been looking for the carbon isotope ratio. And that's because simulations of stellar evolution that most stars are predominantly going to produce carbon-12. So in this plot here, I'm just showing the log of the number abundance ratio of these 2 isotopes as a function of the progenitor mass. And you can see that there are only 2 channels where we expect to produce low carbon-12 to carbon-13 ratios. And these come from either low mass population 3 stars that I'm showing here in purple, or intermediate mass population 2 stars that I'm showing here in gray. And so the key takeaway from this then is that if we can measure this isotope ratio in a near pristine system, we may be able to see the chemical signature of low mass population 3 stars, or alternatively, given the distinct lifetimes of these stars, we might be able to see the timescale on which the system has been enriched. And so now I'm going to focus entirely on the carbon-2 line at 1334 angstroms, where here I'm showing you a model absorption profile for a system that has equal amounts of carbon-12 and carbon-13. And so from this figure, you can see that if you know the line center of this carbon-12 line extremely accurately, then you can start to see the presence of carbon-13 in this system as an asymmetry in the overall line profile. But to do this, you really need to pin down that carbon-12 line using the line centers of other absorption features. So it requires a really accurate wavelength solution And thanks to ESPRESSO, which is the Echelle spectrograph for rocky exoplanets and stable spectroscopic observations, this delicate measurement has now become possible thanks to its unprecedented wavelength accuracy. So at around 4,000 angstroms, the wavelength accuracy is better than 10 to the minus 4 angstroms. And not only that, but this instrument can be employed using all 4 of the telescopes that make up the VLT. So you can really target these faint objects, which is great. So given all this, we applied for some science verification data that came in August of last year. And we looked specifically at the DLA along the line of sight to the quasar J0035 minus 0918. And that's because this system is one of the most metal poor gas clouds that we know of. So its iron to hydrogen abundance is almost 1,000th that of the sun. And it's also a very quiescent system, which helps when you're trying to make this delicate measurement. So here I'm just showing you the absorption features due to some of the metals in this gas cloud. But if we focus on this carbon-2 line, our analysis suggests a distinctive lack of carbon-13. So here I'm showing the ESPRESSO data overplotted with different model profiles for different carbon-12 isotope ratios. And this bright red line here that falls at the very edge of the data corresponds to our 2 sigma limit. So we've found that we can confidently rule out the presence of large amounts of carbon-13 in this system. But given this limit, we can't empirically rule out enrichment from low mass population 3 stars as of yet. But something that we can do is use the entire chemistry of this system to try and model the enriching population of stars. So in this equation in the top right here, we're just trying to gauge the number of stars that have chemically enriched this system that formed within a given mass range where the stars forming obey a power law governed by this slope alpha. And I just want to draw your attention to our estimates on the minimum mass of these enriching stars. And you can see that our estimates are quite different depending on whether you assume this system has been enriched by population 2 stars or population 3 stars. So this grey posterior distribution that corresponds to enrichment from population 2 stars seems to suggest that there has been no enrichment from the lowest mass stars. Which is quite an interesting thing. And it's something that we can use to look at the star formation history of this system, given the lifetimes of these stars. So if we look at the time when we observe the DLA, we can predict when the majority of stars formed in this system. And under the assumption of population 2 enrichment, you can see that following the epoch of reionization, there seems to be a lack of star formation for approximately 1 gigayear. And this is due to the fact we're not seeing the chemical signature of the low mass stars. And so the idea here then is that we can use this tool to look at possible reionization quenching in low mass structures and between the quenching of star formation in this gas cloud and some of the ultra-faint dwarf galaxy population. And so another tentative suggestion that this might be happening is that there's this tentative trend of increasing carbon to oxygen ratios as a function of redshift, which is something that you might expect if you were seeing a delayed onset in the enrichment from low mass and intermediate mass stars following the epoch of reionization. And something that we'd love to do is pin down this measurement further with some higher signal to noise data. And so formative, and we've recovered the first on this ratio in a near pristine system using ESPRESSO. But to better investigate the enrichment of this DLA, we need higher signal to noise data. And our current enrichment model suggests that this DLA may have experienced a hiatus in star formation at the end of reionization. So thank you for listening. I hope you could hear me okay, because I got a warning saying my internet connection was unstable. So thank you.
Thank you. Yeah, it worked.
Okay.
Questions?
Good.
Yeah. Questions from the Slack, please. Let me ask something. So how many more objects do you think you can have in recent and near future comparable to like 0035?
Yeah, you mean a system similar to this, where we could try and do a similar measurement?
To try to get, yeah.
Yeah, it's tricky because it requires the gas cloud to be quite quiescent. So and also for it to be metal poor, which is a rarity in itself. But we're hoping to do some follow-up observations on a further 2 systems across a range of metallicities. So there's at least 2 more that we want to look at, and in the future, certainly with the ELT, there'll be lots more. But at the moment, yeah, they're quite hard to find.
All right, thanks. So Valentina is asking, very nice result. The carbon-2 line looks mildly saturated. Did you take that into consideration?
Oh, interesting. Yeah, so there was some slight contamination with a galaxy in the field with this data, but so we kind of had to account for that as well. So we applied this 0 level to the data to account for some low-level contamination. Yeah. So I think before you apply that 0 level, the line doesn't look saturated. But that's a good question. I can answer that better probably if I look at the data again.
All right, sounds good. Sarah Boltzmann's asking, what would be the best target DLAs to conduct this measurement in terms of their metal enrichment ratios?
Yeah, that's a good question. So one of the reasons we picked them initially is because it had enhanced carbon compared to the solar value, and that's something that you see in the population 2 stars that are most likely descended from the first stars. So ideally we would target things with high carbon ratios and also very low oxygen to hydrogen abundances. That would be ideal, yeah. But and in the future, if we start detecting DLAs with iron to hydrogen that of less than -3, those would be perfect, as long as they weren't really turbulent.
All right. The next question is, can you do something similar in low metallicity stars?
Oh, so you can certainly look at the chemical enrichment with this model of stars, yeah, right, which is something that I'm working on now. Yeah, but then I think you can only do that with population 2 stars. So you may get a bound on the minimum mass of the population 3 stars. Yeah, this so you can use this analysis certainly on stars, which we're trying to do now. But whether you can use it for looking at, I mean, it's not applicable to look at enrichment histories, I don't think, off the top of my head.
All right, let's do one more. So John Weiss is asking, what are the difficulties of looking at Lyman limit systems for similar or a lack of features from population 3 stars? Yeah,
so Lyman limit, it would be great to look at Lyman limit systems too, because then you open yourself up to lots more data. Yeah, but the problem with those systems is that because they have slightly lower column densities, they sometimes they're more affected by ionization. So you can trust, if you have a sufficiently large column density of hydrogen, that your elements are going to reside in like a single dominant ionization state. But as your column density goes down, like with these Lyman limit systems, that's you have to start to think about applying ionization corrections to your abundances.